set up.
Okay, this video is on ray tracing of spherical mirrors, similar to the previous video on ray tracing of lenses. So let's take a look at our three principal rays. Again, we have the parallel to focal ray, we have the center ray, and we have the focal to parallel ray. And so let's set it up for, in this case, we'll do a convex mirror. Okay, so the shape of the mirror is given here with the solid side to the right. Now, this doesn't have to be a mirror that's set up looking just like this. It could also be just an entire ball, right? The radius of curvature for our mirror is right here. And that places our focal point right in between the two. So let's find what that is. And let's look at a ruler to find it. So on this ruler, again, I've set the 12 centimeter mark on the optical plane. And we can see that the radius of curvature in this case is 22 point, it's about 22.4. So we'll put ourselves at a focal length of, so the distance through is 10.4 centimeters. So we'll put ourselves at 5.2 centimeters, which would be right here. So that's our focal length, 5.2. Let's go ahead and write that out. Remember, since rays that come in parallel do not meet, they scatter, then this is given as a negative focal length of negative 5.2 centimeters. Okay. Now let's place an object, and we can put that in an object anywhere we like. Let's go ahead and make it 7 centimeters on the left of the mirror. Now I'll put this at the 5 centimeter mark, even though I said it's 7 centimeters away, so keep in mind that 12 centimeters is our basis, so the 5 centimeter mark here is 7 centimeters away from the optical plane. Let's go through our process again. We can use, again, like we did last time, we can use green to represent the parallel to focal ray, blue to represent the center ray, and purple to represent the focal to parallel ray. Now that's there's nothing special about these colors. I'm just trying to kind of keep our videos consistent. So I'm going to take green here and create a parallel ray all the way up to the optical plane. And then now it's important on your ray trace that we are not going to go all the way to the device itself. We're going to the optical plane. Now I know that's not realistic, but that's actually part of the reason that spherical mirrors have a little bit of blur to them. We actually have to change them a little bit from the spherical shape for that reason. But so this is how we model it, okay, to make sure that everything focuses at the same point. Now this is hitting a mirror, so how's it going to bounce? Well, we've already looked at this from a standpoint of from the radial line there's a normal, and we're using the law of reflection, this thing is going to bounce away from the focal point. So using our ruler, we can put this spot on the focal point. We can extend to where the ray meets the optical plane, and that should be where it bounces off. So we have our first ray. It is parallel at first, and then after encountering the device, it becomes a focal centered ray. Now, unlike our lenses, we don't have a focal point on each side, so you're going to end up using this focal point twice. Keep that in mind when we get to the purple ray. Center ray. Now we're going to look at the center ray a little bit differently here, and actually this isn't one that your book mentions, but I think I like it this way because we have three principal rays that that are true for every device that we use, and we don't have to remember which ones are which. Oops. Our ray can go from the tip of the object to the center of the mirror, and if we want to check and see where it's going to go, all we have to do is check the height of our object. So let's create a length here, like a measure of how tall that object is, so that we can make sure to do the same exact height on the bottom. Okay, so I have a stick here that measures from the line to the point where the rays are emitted from the tip of the object. So if I bring that down to this location right here, that gives me exactly the length that this ray should bounce to. It should bounce to this point. So according to the law of reflection, if the angles are going to be the same, if I didn't go to that point, if I did less than that, the angles would not be the same. If I did more than that, the angles would not be the same. So it must pass that point. Now, when you're done with that, you really don't have to draw anything on here. You could just use a ruler or some kind of measure on your screen or what have you. So I'm going to get rid of that red line now. Okay, and that becomes our center ray. By center, instead of going through the center, it bounces off of the center. Now, let's look at our third ray. Our third ray is a focal to parallel ray. So it's going to end up going parallel, but at first it's going to be involved with this focal point again, right? So if it's to be involved with this focal point, what we have to do is take from that same point of our object and head in the direction of where to use this ruler so that we can stop whenever we want here. And that way we can draw our line all the way up to the optical plane and then stop. Okay, but that way I don't have to guess where my line is going. I know that it's going directly toward the focal point. Now, according to the law of reflection, if a ray is parallel, it bounces away from the focal, and therefore if a ray is focal, it should bounce to the parallel. So now I can use my little horizontal feature here and create this ray. We now have three rays. We're interested, remember, we're not interested in where the rays are actually going as much as we're interested in where they appear to be coming from. So these rays that are leaving the mirror all appear to be coming from a certain point. So what we'll do is we'll take our ruler, and we can actually backtrack this one. That's fine. Let's get our green ray. Where does this one appear to be coming from? Remember, we use a dotted line to represent a ray that is not actual. It's just a virtual ray. We can also trace back our purple to figure out where that appears to be coming from, which is this direction. And we can trace back our blue to figure out where that appears to be coming from. And that one traces back like so. Notice that these all meet at a single point, roughly. It's right there. So this is actually going to be the location of the image. We can double check that using our mathematics if we want to. Remember that we have a object distance of 7 centimeters. So we can check where our image is located at Q is equal to 1 over F minus 1 over P flipped. It's going to give, I know we keep using this equation in the same way over and over. The reason is because it's a little bit more difficult to design a problem where you have to find the focal length or the object distance. So, at least for ray tracing. In your homework, you are going to have to work some of those out. where you have to use, a couple of equations and a little bit of ingenuity to figure out the answers, and that's okay. There's nothing wrong with using a little ingenuity. So 1 over our focal length. Remember that focal length is a negative number. That's important here. And then minus a 1 over 7. And then flipped. So in our calculator, remember you would put negative 5.2 flipped, minus 7 flipped, and then get your answer and flip it. Interestingly, that comes out as a solid negative 3. I think it's like negative 2.98 or something like that. But it's about, I mean, within the precision of what we've been able to measure using this mirror, using this ruler, that's negative 3 is pretty accurate. Okay, so what does the negative mean? Don't forget, image distances are negative when the image shows up where we do not expect light to go. For a mirror, light bounces back. So if the image shows up where the light isn't going, it's a negative image. That means it's inside the mirror here. So we can also figure out the magnification here. Magnification, still negative q over p, is equal to negative of, what's our q? Negative 3. What's our p? 7. So it should be equal to 3/7 the height. That's about accurate. Right? It looks like around less than half, right? The height. And it's positive, meaning that it's upright. Right? Okay, another question that we sometimes ask about these is it virtual or not? And you can actually, there are two ways to tell if an image is virtual. One of them is if Q is negative, then it's a virtual image. And the other one is if your rays of light just appear to be coming from the image versus whether they're actually coming from the image. Okay. You may notice that when we formed a real image with our magnifying glass, essentially what we did was like, how terrible little children will burn ants using magnifying. Certainly not me when I was a kid, just only the terrible ones. Would burn ants with the magnifying glass or set leaves on fire. Also, only terrible kids, not me. Would set the leaves on fire using magnifying glasses. They were forming real images of the sun on the leaves, right? And so we could do the same thing with mirrors. So in our next example, we're going to create a concave mirror, and this is what the legend has it that Archimedes did to the Roman ships in order to set them on fire as they were coming to shore. So we should be able to form a real image if we're careful. All right, let's take a look at another example. But first, let's check how precise we were. We said this is at negative 3 centimeters. So let's double check real quick with our ruler. Plant the ruler down. How close are we? There it is, 12, 13, 14, 15. Pretty close. Not that bad. Okay, now let's move on to our other example. Okay, so here we have a concave mirror with a focal length of 6 centimeters, which I measured out with the ruler carefully. And I'd like to place an object in here in such a way that we can create a real image. So what we'll do is put an object here farther out. So since this is 6 centimeters, why don't we try a 10 centimeter object distance, okay? Okay, as you can see, I've put the focal length at the 6 centimeter mark and that's about 6 centimeters away from our 12 centimeter mark, the optical plane. And the object at the 2 centimeter mark, which is 10 centimeters away from the optical plane. So we would label that our focal length is given as 6 centimeters and our object distance is given as 10 centimeters. Remember, the object distance is always positive, but the focal length, is it positive? Remember, the question we ask to figure out if it's positive or not is, do parallel rays actually meet there, or do they scatter from there? And in this case, parallel rays, when they come into this little concave structure, we're going to they're going to bounce inward, so they're definitely going to meet at the focal point. Okay. Let's start our three principal rays. Again, parallel to focal, center, and focal to parallel. So for parallel to focal, let's go ahead and use our same three colors. Parallel to focal. Let's take a parallel ray here, and remember we're not going to be encountering the device, we're going to be encountering the optical plane, right? So this is theory. So if we go from the optical plane, then we would need to, according to this ray, we'll go through the focal point, right? Let's draw our directionality going in and out. The center ray. Don't forget that we have the same process for this center ray that we did for the last one, which is to say we're going to take our center ray from the tip of the object to the center of the mirror, and then it needs to go somewhere out here. So we're going to make sure that we have the distance correct on this. Here I've drawn our little size for our object so that I can capture that thing and move it down here and make sure that I know exactly how far down this thing is going to go. I mean, if you really wanted to go about the process of measuring this angle with a protractor and getting the same angle out, you could do it that way. I just find this method a lot simpler. So that means that our ray is going to pass that point. Going in that way and out that way. Our final one is the purple ray, the focal to parallel. We have to take a look at this and say, I have to go to the focal point here. That's going to strike the mirror, and again, use the optical plane, not the mirror itself. And then once it goes from the focal point, it should go to then the parallel. So again, oh my goodness, no. Again, ray coming in and the ray going out. Now it looks like these three rays are meeting, and yeah, they're kind of meeting. It looks like the green ray is going to meet the blue ray somewhere down here. It meets the purple ray here, and the blue and purple meet here. So probably we're going to have something around sort of the weighted average of all of them. We would get an image that looks like it's somewhere around right here, right? So we can also go through the process by looking at an object that is inside the focal point. And we would get a different result, right? Before we try that, let's ask ourselves, is this a real image or a virtual image? Is it inverted, or is it right side up? Does it have a magnification of greater than 1 or less than 1? So it has a magnification of greater than 1. It is inverted. And is it virtual or real? In this case, since the rays are actually meeting at that point, it's a real image. You can burn leaves with it. If you burn leaves with it, it's a real image, essentially. Okay, let's move on and try this again. Same focal point, but a different object location. Okay, we've still got the same mirror. We've still got the same focal point. Because we bought the mirror in the same location, or we use the same mirror, which has the same focal point. You can't change that. Well, let's go ahead and write out that focal point. Again, it's 6 centimeters and it's positive. Well, we're going to change our object distance. This time, let's change our object distance to 8. Here, the 8 location, which is the object distance itself would be then 4 centimeters away from the optical plane. Okay. So I'll write that out. 4 centimeters from the optical plane, always positive, right? Okay, so we've got our setup here. Let's go ahead and begin the process. We set up our three principal rays again, as usual. We have the infinite to focal, center ray, and the focal to parallel. Okay, so we have for our first ray, I'll stay consistent here. I've got this green ray. The first two rays usually aren't very bad. It's that third ray that tends to get a little bit weird. So we've got a parallel ray here. When it hits the optical plane, it's going to go to the focal point, like so. Well, that didn't really change much, so that's still pretty much how we would expect. Here's the ingoing ray and the outgoing ray. Let's change to now our center ray. We're going to go through this same process again. Remember, we have our angle's a little bit different now. So we go to the center, and then we're going to be interested in finding an object exactly the same, or a distance, a height exactly the same on the flip side. And that crosses this point. There's the ingoing, and there's the outgoing. Okay, so now the final ray is our purple ray. And this again is the one where we have to be a little bit careful. So we can't go this way. That's just chaos. It's not helpful. And again, I'd like to remind you that is a real ray that can occur, but it's just not helpful in us determining where our image formation is because it never even touches the mirror. So we need one that's going to touch the mirror, but also has to do with this focal point. Our answer is going to be to take one of these to the focal point here, and the other one to the tip of the object. And I'm going to need to actually move this out of the way so that we can see what we're doing here. Remember, this does not come all the way from the focal point. It just seems to because it's coming from the object itself. And we have to go all the way to the optical plane here. So, since we're striking the optical plane here, we now need to take a parallel line going backward because remember, this is a concave mirror, and it causes focal rays to go to parallel to the optical axis. Now you might be looking at this going, well, what the heck, that didn't even touch the mirror. And that's a really good question, if that's the question that you had. And it's important to remember that these three rays are not the only rays that are occurring. They are simply the mathematical way to represent where an image forms. It's actually all the other rays that are going everywhere that actually create the image. But we're not interested in going through the entire process of each of those possible rays to figure out which ones are going to have which particular reflections and having to go through the process of ray tracing every single one of those. These three rays provide us with the power to find where that image forms, even if they theoretically hit the optical plane but don't really hit the optical plane. So let's take these back again as usual. Remember, this one appears to be coming from this direction. Let me go ahead and draw my arrows. I forgot to draw my arrows on there. So since it's coming that way from the mirror, or from at least the theoretical mirror, from the optical plane, then we trace this back on the other side here with an imaginary line. We also trace this one back the direction that it's coming from. Oops. Silly. It's to be green. And we can also trace this one back. Ugh, I did it again. I get excited about the things coming together, so. Okay. These two meet here. These two meet, well, actually about there. These two meet about there, so weighted average is about right there. And that should be where our image forms. Is this real or virtual? Yeah, obviously it's upright, not inverted. Obviously it's magnified, but we want to know, is it real or virtual? Well, the rays are not actually coming from here, so we're actually creating a virtual image, and it's upright. If you run into one of these mirrors, you can do the same thing we did with the magnifying glass in the last video. You can actually walk up to one of these mirrors, and as you're walking up to it, you'll see yourself inverted until you pass a certain point, and then you'll see yourself sort of inside the mirror. That's when you pass the focal point, when you're the object. So when you pass the focal point, then that's when you see the image of yourself flipping from upside down to right side up. So, okay, hope this helps with ray tracing. If you've got any questions, please let me know.